Hello everyone. In this video we are going to look at an example of how to compute Laplace transform of a given function. The function we are given is defined as follows. F of x is equal to, now it's going to be equal to 4 when x is bigger or equal to 0 and strictly less than 2. And it's going to be equal to 0 when x is bigger or equal to 2. So that's the function, and what we want to do is to find its Laplace transform. Of course, Laplace transform of a function is another function, and that function depends on another variable that has nothing to do with the original variable on which the previous function depended. So we're going to represent that variable by the letter s. And so what we want is to find an expression that gives the values of the L of f. So we want an expression of s that is equal to L of f of s. Big question, how do we do something like that? Well, what do we have at hand? We have the definition of Laplace transform, and perhaps what we should do is to apply the definition. Maybe before we start doing that, let's contemplate on the f itself. It's not the usual way of being given a function, and in fact the usual way here maybe wouldn't be very successful, because the function is defined in a different way through a different formula depending on the range of x. So when x is between 0 and 2, the value of the function is constantly equal to 4. At 2, it's not equal to 4 anymore. At 0, it is. And then starting from 2 onwards, the values of the function are equal constantly to 0. So that's the graph of the function. It's not a continuous function. The function breaks at 2. It's what is called a piecewise continuous function, because it's composed of two pieces, both of which are continuous. And when a function isn't continuous, that's not such a big problem for integration, because as long as there are finitely many discontinuities, and the discontinuities are finite, so you don't have the function running up or down to positive or negative infinity, then you could still integrate. And that will be useful because Laplace transform is defined in terms of an integral. So let's recall now the definition of Laplace transform. It's defined as the integral from 0 to infinity of e to the power minus st ft dt, but here, since we are using variable x, let me rather put x. So e to the power minus sx f of x dx, where the f is the function we're working with. Integration takes place with respect to the variable x, and there is also a variable s here, but it's good, it should be, because we are wanting to get an expression that will be a function of s, and that's how this is a function of s. Notice that the s and the x have nothing to do with each other. So since the integration is taking place with respect to the variable x, we're going to treat s as a constant when we integrate. Let us also remind ourselves that the infinite integral, more precisely the integral over infinite domain, is defined as the limit of the usual definite integrals over finite intervals. So we take an integral from 0 to r of e to the power minus sx f of x dx, and we then take the limit of this thing as r goes to infinity. So that's what the infinite integral stands for. Maybe it will be illustrative if we put brackets in here to point out that we're taking the limit of this entire expression as r goes to infinity. Great. So what's next? Well, here we have the definition of Laplace transform, and here we have the function to which we want to apply the definition. So what we want, of course, is to substitute this f into that expression, and then applying the definition, we're going to be substituting that f in here, making use of the explicit formula for f. However, if I do want to carry out the substitution inside the integral, maybe I should rather talk about this part here. If I want to carry out the substitution inside the integral, I would have to decide what to put in place of f of x. Should it be 4 or 0? And the problem is that sometimes it's 4 and sometimes it's 0. So at this point, computationally speaking, I'm a bit stuck, because I cannot just put either 4 or 0 just like that, because x could be between 0 and 2, and if it is so, then the value f of x must be 4, but if it's bigger than 2, then it must be 0. So a general x, we don't know whether it's one or the other, so we cannot make a choice like that. But this obstacle can be overcome by splitting up the infinite integral into two parts, which is a technique that works very well for finite integrals, and it works just as well for infinite integrals. So we present that as a sum of integral from 0 to 2, and then here we're going to put simply copy down this step, not to rush too much to the future steps. We just copy down the expression. So at this step we're simply splitting up the integral into two portions, and of course this rule you could derive yourself based on the similar rule for finite integrals and properties of the limit, but you can also get a nice illustration of it. Infinite integral would be area under the infinite graph. Even though the graph is infinite, the area doesn't necessarily end up being infinite. That's the wonder of infinite integrals. And so when we split up an infinite integral, what we're doing is we're cutting into the area into two parts. So let's say this part is the blue part, and the other one is the orange part. And so the blue part we've got right over here, and the orange part we've got right over there, and the orange part is still infinite, not the value but the integral, and the blue part is an integral over finite domain. And then what we can do now we can actually, I've noticed now that what I've drawn there isn't visible, so let me scroll down. Okay, sorry about that. So there we are. So what we can do now is to substitute f, because you see in the first integral here, in the blue integral, x can only be between 0 and 2, and when x is between 0 and 2, f of x is 4 always, irrespective of the specific x. So now we can rewrite this integral with a specific value for f of x, which would be 4, and then for the other integral, when x is bigger or equal to 2, f of x is 0. So in this integral, x is always bigger or equal to 2, because it should range between 2 and infinity. So that's the same as saying it's bigger or equal to 2, of course. And so since x is always bigger or equal to 2, f of x will always be equal to 0. So here on this side we have e to the power minus x times 0 dx. And now, of course, we run into a very pleasant surprise, because the infinite part of the integral will now become 0, since it's the integral of 0. And just like with finite integrals, integrals over finite domain, I mean, the infinite one will behave the same way. So imagine we've got a function that's identical to 0, and that's definitely what we have here, because it's 0 times something, and 0 times anything is 0. And so then the integral will be computing the area between 2 and infinity under this graph, but of course there is nothing between that graph and the x-axis, not even that blue space there. So the integral will be 0. And then also on the left side we can make some simplifications. 4 can be carried out, and so we'll have 4 times integral from 0 to 2 of e to the power minus s of x dx, and then we have that plus 0. Okay, we can continue the calculation. Now we need to take the antiderivative of this thing, keeping in mind that s has nothing to do with x, so s behaves like a constant. So we'll have e to the power minus sx divided by minus s, and then we do the substitution from 0 to 2. And at this point, we should remark that s cannot be 0, and so we pick it to be anything bigger than 0. Why? Because for the Laplace transform of a function, we want to get a result whose domain is all the values of s bigger than a certain number, and in this case 0 doesn't work, so we want all the s's bigger than 0. Of course, the integral would still be defined when s is a negative number, but we don't include it in the domain because we want domain of the form all the numbers bigger than a certain number. And if it's bigger than let's say -1, that it wouldn't be good enough because 0 isn't in that range, so we pick 0, and then from 0 onwards we are all s's are included. Great, so this can be then simplified to, by appropriate substitution, 4 times e to the power minus 2s, swapped around x and s because now x became a constant, as 2 was substituted in there, divided by minus s, and then we have minus e to the power minus 0, which is 0 of course, and the whole thing is 1. So let me skip into that step. And so then that's divided by minus s as well. And we keep the same s there, and then we can simplify the answer to be 4 times 1 minus e to the power minus 2s divided by s. So that's the expression of s that we were looking for. And now we know that Laplace transform of the function f that we were given, evaluated at each s, is equal to 4 times 1 minus e to the power minus 2s divided by s. And that formula is valid for all the s's bigger than 0. It is also valid for all the s's less than 0, but we are not considering that in the answer because we only want the domain of all the s's bigger than 0. If we did want all of the s values, we could still achieve that, by the way, right? So because even though this step here doesn't work, the step of moving of getting the antiderivative of that thing to be of this kind, this wouldn't work when s is 0, but when s is 0 we can still integrate the thing, right? So what will the integral be when s is 0? In the case when s is 0, so let's first of all copy down this expression. So the question is, what is this integral equal to when s is 0? Okay, when s is 0, this integral, so in the case when s is 0, this integral is equal to 4 times the integral from 0 to 2 of e to the power 0 dx, and that's of course 4 times antiderivative of 1 is x, substituting 2 and 0 there, we get 2 minus 0, and then that is 8. Okay, so a very procedural way to compute this obvious integral. We could then write that the Laplace transform of f evaluated at s is equal to, just like we had a definition for the function f, so it's equal to 4 times 1 minus e to the power minus 2s over s when s is not equal to 0 and is equal to 8 when s is equal to 0. So depending on how we expect the Laplace transform to be defined, whether its value should be a function that's defined for all the s's, or whether it should be all the possible s's where it can be defined, or whether it should be a function defined for those s's that are all bigger than a certain number, we can give this answer or the other one. Okay, so that completes the task of working out a Laplace transform of a specific function. In case you're wondering, in a test or exam environment, or in your submitted homework, which answer you're supposed to give, well, it might depend on the context, but of course the more broader the answer is, the better it is. So this answer we got here is a better answer than the other one, but if you give this answer, that is also fine. It's just that then one kind of keeps in mind that with this answer you wanted to have a domain of all s values bigger than a certain number. So the domain would look like this: interval 0 to infinity, and it's a bit unsatisfying perhaps, because why should we limit the s values when they don't have to be limited, when we can actually deal with all possible s values? It turns out that later on in the theory of Laplace transforms, we're going to do this quite often in various different circumstances to simplify life. So by those standards, then an answer like this would also be considered as a correct answer.